What I decided to do was to talk about two classes of materials which come up, which are, as part of their normal working operation, exposed to very, very high levels of damage. And the two I'll pick actually are batteries, the kind of thing you have in your cell phone. You typically charge and discharge very large numbers of times and it changes enormously. And nuclear materials, things that are in the core of a nuclear reactor, which have very, very high levels of radiation damage. And I think they might be interesting, but I'm not sure, as sort of interesting paradigms of what I think of as an engineer as strategies. And I think the two strategies have been discussed. You can either have materials which are extremely robust and therefore are difficult to damage entropically, or you can have repair strategies to fix things, and maybe you need both. But in the area of science that we're talking about, we're sort of very, very far behind biology, and I'm looking for inspiration actually from biological principles about how to design better new materials and better batteries. But I presume if I press on some of these things, something moves. No? This doesn't connect? It just points? It doesn't? Well, no, I don't want a pointer. I actually want it to move, because otherwise I've got to find this darn button, okay? Is that one? Sorry. Nothing like PowerPoint to do this. Sorry. Well, okay, so look, here's an example of a sort of nuclear material. And by the way, this is part of what is quaintly called in the nuclear business life extension. We haven't been building nuclear reactors for a while, so they're coming to the end of their official regulatory age, whatever that means. They were designed, or somebody said that they'd work for 40 years. Nobody really knows how long they will work. But since we're not building nuclear reactors anymore, we'd like to actually make the ones that we have last longer. And what stops them working? Well, cracks. I mean, so the inside of a nuclear reactor is a rather forbidding place. It's very hot, it's very corrosive often. And in particular, you have very high levels of damage. And this is a piece of a fuel rod. This is a piece of a fuel rod which has been put there for a long time, long enough that it's been irradiated to what's called 70 dPa. So that's 70 displacements per atom. So that means that every atom in that has been whacked 70 times, kicked somewhere else. Right. And the interesting thing you see is actually that the material looks kind of the same. It's a little bit pitted, but it's actually bigger. Right? It's swelled. And at that point, what happens is people get scared and they take it out of the reactor. By the way, at that point, it's only used about 2% of the fuel. And it would be nice to keep it in longer, because as far as it's just sort of conservatism that sort of presents it going. Can we try that? Oh, thanks. So this is, by the way, what happens if you think about what actually happens when an atom gets hit inside the solid. And this is actually a simulation, and you see that there was one collision, there's all of these things, and each one of these things are atoms moving around. And you create a huge amount of damage, but it anneals. So, this is early stages. You see this cascade going through vast amounts of damage. There it goes, and then it comes back. Materials, by the way, are extremely robust. The point that Bob was making is that this is a solid. Its ground state is a crystal. Okay? You do stuff to it, and it tries to get back to the crystalline solid that it wants to be. Entropy doesn't grow. It's the minimization of the free energy. Right? Okay. And now you can see actually that there's stuff left around, and that's actually kinetic. If you click to the next slide, you can see what happens after it settles down. So even though there are these displaced atoms, after a while, they arrange themselves into nice little ordered structures, which again minimizes the energy. And these are pores. This is a scale of a few microns across inside this in terms of the material, and that's what swells it. But the material actually is remarkably robust. And strategy one, actually, for building long-lived materials is to make use of the innate physical properties of the material, that they don't like to get damaged. The idea that entropy always increases is, of course, true in a global sense, but it's not necessarily true for the specific thing that you're looking at. Try again. Sorry to have you sat here. So second example is something that you all own, which is a battery. This is a reminder of how a battery works. It's very simple. You have an anode. In your cell phone, you have graphite. You have a cathode. In your cell phone, it's something which is like lithium cobalt oxide. And what you can do is it's just a chemical reaction that lithium will flow from here to there. If you are, however, you make sure that there is no electrical contact so that no electrons can move from here to there. As the positive charges move in here, in the external circuit, the electrons flow, and that's what you get out. And if you want to charge it back the other way, you pump the electrons in the external circuit, and the lithium ions move back. This happens in a battery, and it's just a chemical reaction. You take this and you go from there to there, and you just separate the chemical reaction into two halves, and you make sure that the electrons go in the external circuit, and that's how a battery works. Okay. It's reversible, formally. So, in principle, in principle, as a matter of chemistry, I can cycle this back and forwards as many times as I like. And if I do it slowly enough and everything stays close to equilibrium, this is fine. Okay? Now, no, the goal, by the way, of batteries is to make them both very high capacity, and that means that a lot of material needs to shuttle around. So having a lot of material shuttling around means actually that the physical structure of this material changes. If I remove all of the lithium ions from this structure, it collapses and goes into some other stuff. And I'd like to do that more and more. So that means that I take the lithium out and I go from lithium cobalt oxide just to cobalt oxide. In fact, you don't go anywhere near that far because it's too damaging to the material. The material will get damaged and fall apart. But nonetheless, as a thermodynamic thing, in principle, this is completely reversible. And the challenge is to make things that work long. So please go ahead, thanks. So this is a slightly scientific American view of that slide, but it's just describing that. And sort of gold materials which have much higher capacity, like silicon rather than graphite and things like this. But remember that in order to have impact in the battery world, you need to do two things. You need to have higher capacity. That means more material change. And the other thing is you'd like the batteries to last a long time. Right? So click again. But actually, what does your battery really look like? I gave you that scan. If you prise open your cell phone battery and look at it inside, this is the anode, this is the cathode, this is the stuff in between. It's a complicated, awful mess. And we got to this complicated, awful mess by a kind of evolutionary process that has put all kinds of other things into these batteries to make them work better. Most of which we don't know what they are, and most of which were done on a lab bench by people mixing stuff and saying, well, let's go that way. So it's Bob's point again, that engineering actually is a messy, random evolutionary process. And it has an evolutionary driver, next click, which is money. We'll get to, but but as I say, here are the problems, right? So I own an efficient battery. I need to cycle it very many times. Practical point is that I gave you one reaction which can happen. If you put stuff together, other reactions can start happening. Okay? So there are side reactions, and that often sends the stuff off into pathways which are unpleasant, and you get materials made that you don't want. So you need to have something that will come and eat them up, kill them. Okay? We want to cycle it a long time. Okay? So the pressure on cycling, we've already heard about engineering. If you want something to last a very long time, you're going to have to invest a great amount in engineering it in the early stages so it will last. Okay? We have a complete failure thing, and also we like failure modes which are gentle. We'd like our batteries actually not to die. You want a battery which senesces gently and goes out. So these are all sort of principles you would like. So thank you. Sorry, actually I could probably click this just as well as you can. Yeah, thanks. So evolutionary process, right? So firstly, we've got a $10 billion business. It's an appalling technology. It's the worst of our electronic technologies that we have. This is the new MacBook. If you take the back off the MacBook and look at what's inside, it's all battery, right? The logic board is really tiny. There's a screen which sort of has to be big because you have to see it, but it's incredibly thin. Everything else, the whole of the weight, all of this is actually battery. And it's running at around 1% of theoretical capacity. Okay? And now you see the evolutionary pressure on this because and the evolutionary pressure produces money. And there are other problems that we'd like to address, like if you wanted to back up renewables with solar, the amount that you would need if you wanted to do it now is 1,000 times the annual production of these lithium-ion batteries, so you didn't really run a lot of them. Or you could have 10 Hoover dams with the annual power of the Hoover Dam operating every 12 hours. But the goal, of course, is to turn batteries, not to turn money into batteries, but to turn batteries into money, because the goal is if you actually have an efficient battery, then it's a bank, right? And this will change everything. So the evolutionary pressures now produce a sort of a huge explosion of activities of trying to make better batteries in different kinds of ways. And there are people who approach it from a very principled point of view, like the fundamental biologists. And there are people who approach it from, I shouldn't say an unprincipled point of view, but a point of view which is very different. And there are far more of them. And they're doing evolutionary experiments because they're sitting in labs and they're trying to tweak things and make it a little bit better and to move where we go. And the interesting thing about the battery business, it's a competition between people who think hard and people who work hard. And typically what happens is the hard workers who come in larger volumes and get rewarded who do well. Okay? Now, just as a very small example of the second strategy of how to make something live long. That is, the rudiments of what one would like to do in biology. So one thing is if I want to have stable battery materials, an anode that will reform, I could choose a material where that anode is the bottom of a deep thermodynamic minimum. So that I can pretty much guarantee that the thing will reform it in its own way. The other thing you could do is you could say, well, there's all of this stuff going to go on inside and the system is going to break, and I'm going to start fixing it piece by piece. I'm going to engineer things that will work, and I know that, let's see if I can succeed in playing this. I mean, this is just a cute thing, but it's done from some work coming out of some colleagues of mine. Now, which button do I hit? Oh, no, that was the wrong one. Ah, dear, never do this as a theorist. Now all I have to do is to figure out how to get it to play. Yeah, that's right, but I've got to hit the play button. There we go. It requires skills that I don't possess. No, you still need to... there we go. So this is actually a battery connected to... doesn't matter that there isn't any voice in it, but actually what's the strategy here is that you're just trying to make materials where the conductivity will restore. And so what you do is that you provide capsules of stuff which are inside so that if you cut the wire, they fill it. And so, here's an example of, you've sort of broken a circuit just by sliding through here, and a little while later, it reforms. So you build in autonomous things, making the use of, physical properties to try and gradually engineer your way around problems. So the reason that batteries now begin to look complicated is that you don't want that to happen. So why does that happen? And the reason that happens is that you've got in your batteries, you've got lithium. And lithium is a metal which, if exposed to air, catches fire. And so you don't want to either expose it or to form filaments of lithium. So you need something that if something bad starts happening in here, Then it begins to develop a short. As it develops a short, the temperature goes up and it gets a runaway. So you have something that melts when it gets hot. And when it melts, it quenches that flow and it makes the current go somewhere else. Okay? So that's the kind of thing you've got in here. You can functionalize small materials which go inside so that, again, so that they start dealing with damage which comes as a result of cracks. So if you form a crack across here, and I think that was the thing you were just seeing, then you just put some stuff in that it gradually oozes and fills the spot. Okay. This is not very advanced. Given a sufficient amount of evolution, people will sort of find their way in a sort of a moderately thoughtful or less thoughtful way to track down all of these changes. But I mean, I think I do want to echo again the point that Bob was making earlier, is that engineering, I think, is not so different. The way engineering happens and the way we proceed through these things is not so different from the way biology does it. Biology has a much better toolkit. And one of the questions I have about a strategy for building better batteries is there something that you can learn about an engineering process which you can take from an evolutionary process? Is there a way that you could take the ideas that you're talking about in terms of aging, about how an organism which is supposed to perform a fundamental function in a particular way, it's evolved a strategy for doing that which you could express in a sort of a broad network, and to do the same kind of thing when you're talking about physical materials. And as I say, the interesting thing to notice about materials at the moment is that we're moving away from the paradigm of finding a deep thermodynamic minimum in which to live, in which case I don't need to care about entropy, to moving into a mode which is much more like biology, where you need to assume that because you're trying to do something complex and flexible, there will be irreversible processes that are difficult to get rid of, and therefore you want to continually engineer around those in a way which begins to look a little bit more like biology. But that's your entertainment before lunch. And I'll stop. Thanks.
So, questions?
Pretty random, huh?
Bob, I can't have kept you quiet.
Well,
Bob, while you're thinking, let me give you the microphone.
yeah. Right. For the benefit of the audience, I want to ask a question about the difference, if any, between a physical repair mechanism and one that's engineered. In other words, in your view, is there any difference between something that repairs itself using laws of quantum mechanics or whatever is going on in the metals on the one hand, and something that repairs itself through engines that are through engines that burn ATP or burn something that are dumb?
Look, my own view is that I don't see a distinction between those things. There's, of course, you can. Maybe there's a distinction in principle about dealing between a closed system and an open system. If, in order to repair something, I have to feed it, it has to eat, then I'm naturally transferring energy through that process, and by doing so I'm doing something which is thermodynamically different from having a closed system with stuff which is just going to get used up. But as far as I can tell, in practice actually, most of biological processes are operating very close to thermodynamic equilibrium, so that the fact that repair is going on does not by itself generate damage. By the way, that's now a question for you. Right. So in principle, you can say, when I've got an organism and I'm eating, I'm doing work on that system. As a result of that, I'm going to make things happen just because I'm doing work. not because I've established some process that I want to fix. And I think that work that is being done on the organism is negligible. But that's an opinion, and I don't really think I have a view. I mean, so I'm asking it back. So in that case, it really is the same. So.
Yeah, I'll talk a little bit about that tomorrow.
Right.
It costs a certain amount of energy to do certain things.
Right.
It depends on how accurate and how fast you want to do it.
Right, exactly. So I think so if you're operating, slowly enough, right? As I say, I can guarantee, by the way, to make a battery, which is I can cycle 1,000 times and is completely efficient, providing I do it infinitely slowly. Which ain't practical.
But so this is exactly the point in biology, that you don't want infinitely slowly, because you'll be making a lot of errors going back and forth.
Sure.
So you want to drive the system out of equilibrium.
Yeah.
And do it faster.
Yeah, but the thing is, I'm not sure I want to drive it that far out of equilibrium, because most of the processes that I'm talking about here are in the end kinetically dominated. And the kinetics are just lifetimes long, so that's why you need a repair mechanism. I could, of course, reconstruct in principle the stuff by heating it up, cooling it down, recrystallizing everything, but that wouldn't be a way to go. But in fact, yeah.
But so the ATP would hit up an order of magnitude higher than KT,
for sure.
the local temperature.
Yeah, and I, by the way, I think a very good question for practical associated materials is, should we try and design nanorobots to get in there and fix things in a smart way? I think that's the question. And I don't know, actually. I'd like to get an answer from this meeting.
Yeah, hold on. Just one thing before I give you so it's very interesting that in biology the DNA is in a one-dimensional structure, so you have access.
Yeah.
Electric eels live about a decade or possibly more, and apparently store electricity in what is tantamount to a battery. Is there anything known about how they do the kinds of repairs that have to be done as you described in order to maintain the longevity of those batteries?
I mean, I think that's a good. I think that's a good question. In fact, I don't know how electric eels work. It would be a good. It would be. It would. That sounds like a nice thing to study. I don't know. I like that idea as a thought, because you see, it's interesting if you look, by the way, at technologies for
solve some of these problems.
Yeah. Well, so it's interesting if you look at technologies, by the way, for renewable energies and things like this. There are large numbers of them where solutions in principle have already been given by biology, right?
Yeah,
So we actually have, we have solar cells, we have solar to fuel, we have refrigerators. All of these things biology has learned how to do. It's quite difficult to do batteries, and the reason is that we're surrounded by water, and water conducts. So there are special challenges actually in biological systems for doing batteries. And I don't know about the electric eel, but many things which of course are used to produce electrical impulses are transient, and they're a result of chemical reactions across membranes, right? But they're very transient, and you can't store an electrochemical potential difference without doing a continuous amount of work, because there's a large leakage current. So if the electric eel is fixed how to reduce the leakage current is a good question.
There is a literature on their electrical storage ability that might be interesting.
Yeah, no, that's a fascinating idea.